Yeah. Okay, we are live.
Okay. Okay, I'll go ahead and start then. So, hello everyone, and this is our 19th lecture of I Technical Lecture Series, and we are extremely happy and delighted to have Dr. Who is a lecturer in phonetics and phonology at Newcastle University. She has received her doctorate degree from University of Oxford, and after which she worked as a TTS language engineer and a linguist at ALAB, Rokid Inc, where she worked on various tasks for developing text-to-speech system and led a project for developing a singing TTS, and which I think is amazing. I have to look more into that to know like how what the process was. Dr. Kong's research covers aspects of speech prosody, and she is also interested in bridging the gap between linguistics theories and speech technology. And I am really looking forward to this lecture. I will let Dr. Cong take over from here.
Hello, everyone. I'm gonna start my presentation now. Can you see my slides? Yeah?
Yes.
Yeah. Thank you so much for inviting me. This topic is something that I've been interested in for quite a few years already. And I hope what I say today can attract more discussions around this topic and potentially more collaborations. Yeah, so I'm going to start. So I am a linguist. Before I go on, for anyone who is not familiar about what linguistics is, here's a definition. So what is linguistics? Linguistics is the scientific study of language. And the word linguist has two meanings. One meaning is, refers to people who can speak multiple languages. But here, what we mean by linguist here is the people who apply the scientific method to conduct formal studies of languages. Some people prefer the word, the term language scientist. I think that's a very nice term as well. For me, I am currently a lecturer in phonetics and phonology. To put it simply, I study speech sounds. So that also means I'm not that familiar with, say, syntax or grammar or semantics, that side of the things. So over the years, I've wondered what linguists do in speech technology industry. So I've gathered some information about it, and I would like to share with all the audience who come from a linguistic background and would like to work in tech. Of course, this is just my little summary. Maybe I can't, I don't cover all the roles. So the first role is language engineer, which is usually they're a language engineer in a specific language, and they can provide the language-related information. Here is a recent advertisement. So this summarizes the responsibilities and the skills that you need to have pretty nicely, I think. And the second type is data administrator, the data lead, basically, in the company. The data lead might need to design speech materials. They might need to go and record new speech data, and they might need to design and manage the annotation, and so on. Basically, everything about language data. And the third role is quality assessment, QA. For instance, in a TTS setting, this means listening to the synthesized speech and then point out the bad cases and then possibly even propose solutions. And the last one is project or product management. If there is a certain project that a linguist can lead, for instance, the Singing TTS I was talking about in my previous company, then a linguist can also take on this role. Of course, there are more roles for linguists in NLP, but as I said, I'm not too familiar with the field, so I'm just gonna skip this part. You can explore more. So now we come back to our topic of applying linguistics knowledge to speech technology. There are some questions I ask myself all the time. Now I try my best to give some answers. Of course, these answers are very dependent on my personal experience and may not reflect the whole truth. So the first one is linguistics still used in speech technology? I know there's a lot of use for NLP, but now we only talk about TTS and ASR. I think the answer is yes and no. So yes, in the sense of what I just showed in the previous slides, there are so many roles for a linguist, but no in the sense of the more up-to-date research results from linguistics are usually not used in speech technology. So yeah, that's a pity, I would say. And the second question I ask is linguistics still needed in speech technology? This is, well, after working in industry for over a year, my answer for this is yes. This is probably why I came back to academia in the end. But I also know many engineers believe otherwise. I think this is mainly due to a lack of communication. We're all in our own information cocoons and we do not know each other's research that well. So I think, yeah, this collaboration, this application of linguistics in speech technology is still at its baby stage. And it needs a lot of efforts from both sides. And there surely will be many detours we will have to take before we get to the final destination. But this is a part of research. This is a part of innovation, right? And the third question is, how should we apply linguistics knowledge to speech technology? For this one, I don't really have all the answers. I wish someone could tell me. But I have also made a first step trying some things out. And today I will show you my effort. So yeah, this brings us to my topic today, applying featurely underspecified lexicon phonological features in multilingual text-to-speech. So let me introduce some background here. Many latest modeling in TTS systems adopt language-specific phone labels, such as for English is alphabet, and for Mandarin is the pinyin system, which is the Romanized system for Chinese characters. However, using this system means every time you want to add a new language or develop the system for another language, it requires altering the front end extensively. So how do we avoid that? One solution is to use a more common set, which is IPA, International Phonetic Alphabet. However, for IPA, it still has more than 60 labels. Using phonological features will greatly reduce the number of labels. Therefore, we propose an input system based on phonological feature series with an aim to progress towards a universal TTS system eventually. So progress towards, that's the keyword. So distinctive features are designed to describe the phonological system in the world's languages. So in this study, we look at one of the feature series, the featurely underspecified lexicon full model. This model defines a minimalistic inventory of distinctive features that are necessary and sufficient to describe contrast between phonemes in any language in the world. It has been tested extensively in human speech perception in different languages, for instance, English and German, and it's also been tested in child language acquisition and also loanword phonology, also automatic speech recognition and production to some extent. So this is a very robust system, feature system. That's why we adopt this version of it. And then let's talk a little bit more about the ASR application. This is actually a project led by my supervisor and her colleagues. And then they, sorry about the order. This system can both detect mispronunciations and provide corrective feedback for second language learnings. And the authors address the question of whether phonological features can be used effectively in an ASR system for pronunciation training in non-native language learning. And they used German and Italian learners of English. And if you go to this link, there's a video of one of our colleagues using the app as well. There's a more technical paper as well, and I'll leave the details here. So the model structure in this paper is basically you have your uttered speech, and then you straight away have the phonological features here, and then it goes through a list of models, and then it has two separate branches for substitution and deletion detection, which tells you which phonemes are mispronounced. And also you have the feedback construction, and that gives you the corrective feedback. I think this is a very cool system. And then after looking at full applied in ASR, let's have a look at some TTS studies which used features. So the first study, they used English and Spanish training data and then synthesized German successfully. And then the second one, they used a set of 6 languages. And in the end, they found for the more typologically similar languages, when the test language is more similar to the trained languages, then you have a higher MOS. And when the test language is more typologically distant from the trained languages, then you have a low MOS. It's quite low. And then for this study, the third study, they used English and German again. And then in the end, the result showed when the training data have 14 hours of English and 15 minutes of German, the naturalness is similar to using 4 hours of German only, because the test language is German. The last one I think is very interesting. It used a lot more languages, and it also tested 3 different feature systems. And 3 out of 5 test languages showed advantages over the phonemic baseline model. The phonemic baseline model is basically, I can't remember exactly what they used, but it's either IPA or the SAMPA, that kind of phonemic input. And for the 2 that were not as good, is because there were some feature missing, if I remember it correctly. And a little bit more about the full full model. This is the feature geometry. We have 4 base root features, and then we have the manner of articulation and place of articulation and the laryngeal node. So in total, it has a very small inventory of features. So only around 20, depending on the languages that you use. If your languages are very similar, then maybe you don't even need this 20. So maximum 20. And because you can see these are very articulatory, basically the biological aspects of our pronunciations. Let's put it that way. So it can represent the world languages very well. And all the features are monovalent, and there is no dependent feature in this organization. And consonants and vowels share place feature. That means they don't have to have two separate systems, which can reduce the number of features. And because these features are somehow articulatory, they are correlated with acoustic the acoustic properties of speech sounds as well. So yeah, it has many benefits. And these are two tables about the features in English and in Mandarin, because we ran the experiment between English and Mandarin. So that's why we only have English and Mandarin. And this is the binary table that we use for the computational modeling. And we built a modified TTS model based on fast speech. We changed the phonemic embedding input to a text embedding input. The input text contained sample phonemes, prosodic features, that is prosodic phrasing features, and lexical tone features, since Mandarin is a tonal language as well. The sample phonemes were then converted into corresponding binary features using the mapping we just mentioned in the previous slides. Prosody and tone features were also converted to prosody and tone embeddings, respectively. And then we ran two sets of experiments. The first set used small data set, which has like 0.5 hours and 2 hours and 8 hours of speech. And then the second one is a much larger data set. It uses 100 hours of data. So for experiment 1, we only use the small data. It has one Native American English speaker's data, which is 2.62 hours. And the Mandarin data, we put them into by steps. The first time we only put it in 0.5 hours. And then the second step, we put it in 2 hours. The third step, we put in 8 hours. So that generated 3 models. And the M0.5 one has the English data. All 3 of them has the full set of English data. And then the 0.5 has 0.5 Mandarin. 2 has the 2 hours of Mandarin. 8 has the 8 hours of Mandarin. And results. So we got some MOS, the mean opinion scores. There are subjective ratings of intelligibility by native listeners. As you can see, the scores can be very low for some models, especially the 0.5 ones. But for the English, it's pretty good at the English voice. It generated the English sentences with a very high intelligibility. And for the Mandarin data, for at 8 hours, it can generate Mandarin sentences pretty well. And for the code switching one, the 8-hour data, the 8-hour model can also generate pretty good code switch data. Yes. Let's look at them one by one. For the English utterances, yes, since the input data contained 2.62 hours of native English speech, the English voice has very, very high ratings. for all three models. We can have a listen. If we listen to the 0.5 hour one.
My mother is making a bed.
Let me know if you can't hear it.
My mother is making a bed.
We can hear it. This is
Great, thank you.
Yes.
Yeah. And for the 8 hour one.
My mother is making the bed.
So you can hear the part is clearer than the 0.5 one.
Yes.
My mother is making a bed.
Yeah.
Yes, definitely.
And for the for the Chinese voice, it really can't do it because in this model it's mainly the English data, right? And the 0.5 one is very low. Even the 8 hour one is not very high, but they managed to create the output does present an English-like speech rhythm. Let me show you this first.
My mother最顶得的. My mother最顶得的.
I know maybe at this point you're thinking, no, it doesn't have English-like speech rhythm, but listen to the first one.
My mother最顶得的. My mother最顶得的.
As a bilingual speaker, I think this first one sounds more Chinese than English to me, but this one I can kind of tell that it's trying to speak English. Yeah. And then for the Mandarin utterances, in the point 5, it can also only vaguely produce the Mandarin utterances. Some words were intelligible, but not all. And both of these small models have all sorts of issues. But for the 8 hour one, it can already reliably produce intelligible utterances, despite some small voice quality issues.
明天我们同一时间相约直播间再见.
This is pretty good Chinese. I know you probably don't understand it, but it's okay. But you probably can hear some voice quality issues there as well.
明天我们同一时间相约直播间再见.
And for the English, it still cannot produce intelligible Mandarin utterances in any of those three models. However, if you already know the text, you can identify it.
Missing moment from Eastern and Nichbochian. Jijian.
Yeah. Especially if you hear the last part, it's supposed to be 再见. It's saying 再见.
Missing moment from Eastern and Nichbochian. Jijian.
Yeah.
Yes. Sounds more English.
Sorry?
It sounded a little more English.
Really? Yeah, because it doesn't have any of the lexical tone specifications. Yeah. So here we look at the code mix utterances. In the 0.5 model, neither of them is good, but the M2 had some improvement. For M8, it's much clearer.
明天的presentation 你背一下吧，一定要弄得很危险。明天的 presentation 你 prepare 一下吧，一定要弄得很 amazing.
I don't know whether out of context you can identify the English words. So it's 明天的 presentation 你弄一下吧，一定要 what? Sorry.
明天的 presentation 你 prepare 一下吧，一定要弄得很 amazing.
Presentation, prepare, amazing.
Yes, I could totally hear those.
Yeah, so yeah, that's pretty good. Actually, as a Chinese speaker, I think this English speakers' utterances are pretty near ideal, but because it doesn't have any lexical tone specification, that made people think it's not as intelligible. That's probably also why you thought it sounded more English. But this is like exactly like an English speaker trying to learn Mandarin. They usually don't have the tones that well, and they sound like this. That's very interesting. Yeah. And for experiment 2, we finally got to a much bigger data set. We have 3 native English speakers data, which has 9 hours luxury. And we have 9 Mandarin speakers data. There's some L2 English speech, and there's some code switch speech, and there's some native Mandarin speech. And we used 3 voices to synthesize the utterances. One is a female voice. It has bilingual data. She is a native Mandarin speaker. And another one is a monolingual Mandarin speaker, male voice. And the other one is the same English speaker who has only monolingual data. And then the results, we calculated the phone error rate. It is an ASR-based objective measure with Char-Siu textless phonetic alignment tool that we created. I put a link there if you're interested. It's a very nice tool. And then we also got the mouse. So here you can see the bilingual speaker has very good performance. And the monolingual Chinese speaker didn't do that well in English, but still a lot better than what we saw just now. And for the English, it's vice versa. They didn't do very well in the Mandarin utterances, but still better than the previous one. And here, let's have a listen. This is the monolingual Chinese speaker.
My mother is making the bed.
This sounds a little bit weird because the voice itself, the data recorded for with this voice are data for advertisement, like if they want to sell something. So he's a very passionate speaker. Yeah.
My mother is making the bed.
And yeah, from here we can see even the style has been transferred, so it's very good.
My mother is making the bed.
And then the next one, this is another not that good one.
明天我们同一时间相约直播间，再见。
This is already a lot better than the small data set and very intelligible.
明天我们同一时间相约直播间，再见。
And this is a good one.
明天我们同一时间相约直播间，再见。
This is like perfect. It even has all the prosodic features that it should have.
明天我们同一时间相约直播间，再见。
And this is a code switch one, and it's pretty good too.
你的 Android 为什么那么快？我的 iPhone 好慢呀。
I don't know whether you can identify Android and iPhone.
你的 Android 为什么那么快？我的 iPhone 好慢呀。
Yeah.
Sounds very good.
Yeah. So.
My mother is making the bed.
Yeah, this is this bilingual speaker speaking English. I don't know whether you can tell, but to me, it has a very thick Chinese accent. Actually, for both the Chinese speakers, when they speak English, they both have very thick Chinese accent. This is another amazing thing that because it's using the feature theory, it is identical with language acquisition. Let me show you how this is done. So yeah, finally, after showing all the results, we can see, okay, full features are feasible. Now we're using very small data and not fine-tuned models, but we already can generate intelligible sentences. So in the future, if we work more on it, it should have a lot of potential. And yeah, this is what I was saying just now. They exhibit human-like L1 and L2 acquisition patterns. So for human processing, listeners first extract the features from auditory input from their L2. And then they extract the L2 features. The extracted L2 features are then mapped onto the underlying contrast of the listener's L1. and then the listener or the speaker add the phonological rules from their L1 to produce their L2. That's why they have this thick accent. So yeah, I think when I realized that's what happened, I was very happy with this. So yeah, can linguistic theory be applied to speech technology? I'm actually curious to know your answers now. Well, my answer is yes. And I think it's mutually beneficial because TTS can be trained on low resources if we use this method. And the phonological theory of full can also be supported with a real-life application, which is nice in both ways. So this is so much about this study. And what other types of linguistics input can we offer? So one type of it, another type of it is assessment. So the QA aspect. Basically, you offer what is the problem, why is it happening, and how can we improve it. As I just said, in my previous company, we did a virtual singing platform. So that means for the input, the users put in the lyrics and the musical notes, and then the system can generate an AI sang song. It's kind of similar to these virtual idols. I'm not sure whether you're familiar with them, but they're very popular in East Asia. But they used an older technology for synthesis. The model we used in our previous company was an adapted TTS model trained on speech data. So speech data is different from singing, right? When we talk, we never lengthen a syllable to like la, we never go that long. So it is bound to have bad cases. I'm going to go through this part really fast so we can have more time for other discussions. So let me show you a bad case. So this is only one verse from human singing, and this is the text to sing. This is a bad case on the second syllable because it's shorter than the other ones. And what I did was pull them into prod and look at them look at the spectrogram and waveforms. And then I found the proportion of the synthesized singing is different from human singing. So here the consonant is much longer than the let's call it rhyme. And for human singing, the consonant is shorter. But for human speaking, that's actually what the proportion should look like. That's why in synthesis singing, it just used the duration you learned from human speaking, the speech data. And then if I modify it to follow the pattern of the human singing, then the sound sounds a lot nicer. So I have come up with a few research questions. When a syllable lengthens, does the segment lengthens proportionally? What are the factors influencing the ways segments lengthen? And is it phoneme class or skeletal slots? And I have divided all the bad cases into different categories. And for the full results, because it's too long to present here, I'm just going to put the paper here. If you're interested, welcome to contact me, and we can talk more. And another bad case, that was a duration bad case, and this is another type. This is a rhythm bad case. Again, this is in Mandarin, so I don't know whether you can hear at some point the metronome started beating, but the sound came after it, so it sounded that it missed the beat. So this is bad, and we tried to solve this problem. So we came up with the research questions of the first one is beat presence, which types of phonemes attract beats, and the second research question is beat alignment, like where do beats align with the segments. Again, I'm going to put some information about this other paper that we have. It talks about that. So yeah, for future research, this future study, we still need more languages. Now we only have Mandarin and English. We would like some more languages with rarer features to test how robust the system is, and also better control the experiments. Our steps are not even, so yeah, we also want to see how small the data sets can be to train an intelligible system. And then we also need to fine-tune the models, because now the models we use are essentially designed for the phonemic input, but we only replace the input into to the feature input, so they're not really fine-tuned. And for the singing studies, now we have linguistic conclusions. From my research questions, you probably can see they will give you a list of factors or some coefficients, but how do we use these numbers, these conclusions in speech technology? That's another thing that I need to think about. And if any of you have answers for me, very welcome to contact me and tell me about it. Or if you're interested in this line of research, we can always do it together. So yeah, finally, thank you for listening. And I wish I was able to answer all the questions I raised at the beginning, but at the moment, I can only initiate the conversation. Hopefully, in the future, more and more people will join the discussion, and let's work on it together. Yeah.
Thank you so much. I think I was really I was listening to every bit of it, and it's really fascinating, especially because I'm because of my own background in research, I'm more interested in phonetics and its role in speech technology. So I will, before I ask my own questions, Shishir, do we have any questions from the YouTube channel?
No, we don't have. We have only one question that I only asked that, so I can ask that.
You can just go ahead. Yes.
Yes, yeah. So you can maybe read out those questions from first, yeah.
Sorry, I was muted. Okay, so I have some questions, and the first, what motivated you to venture deep into linguistics and speech research? So there are 4 questions from Rustam. I will just go one by one, if that's okay.
Yeah, so that's a very long story that I should start from when I was 13. Yeah, because I went to a foreign language school for junior and high school. And then after that, I naturally went into a foreign studies university, and I studied English for my major. And yeah, when we chose the directions, I chose translation and interpreting. But I'm the type of person who I just don't really like the practice of it, but I like the theory of it. And because I don't like the practice that much, I always think, oh, when can computers do that? How can they do that better. So I wanted to learn more about language itself to see how these computational models can improve. And I went into linguistics. And then I studied language acquisition, and acquisition again is not theoretical enough at that time for me. So for my DPhil, I just went into a more theoretical field. It's called phonology and phonetics. And then, but after my DPhil, I started doubting myself. I thought, what are we doing here? Are these theories actually useful? Or are we just kidding ourselves? So I decided to go into industry to see how things are used in real world. And while I was in the company, I realized, yes, we still need theory. We still like these, you can always pile up more data to make your model better, but that's not the best way, in my opinion. I think because we're human, we're not machines. We have an advantage over the machine for being able to think about the meta knowledge itself. So yeah, to think about language itself. So now I'm back to academia, trying to figure out a little bit more. Yeah.
Honestly, I think this is the best answer to the same question I've heard, because it's a very frequent question that people get. And yeah, I really thank you for such a well-explained, honest answer. And so the second question is more technical. So he has asked, which toolkits have you used and would like to recommend to other fellow researchers?
Yeah, because I'm not I'm not an engineer really. I'm a linguist. I usually don't train models myself. I have collaborators who would train models for me. But I really want to learn how to do that. That's another honest answer. I saw this question yesterday, so I prepared a few slides. I mainly use the tools to do phonetic research. I'm just gonna share my screen again. So here, the textless forced aligner I just mentioned, I think is a very good one. I know this is like self-advertising, but because I really like it, I would recommend it to everyone. Because it's not a simple forced aligner, which you have to put in the sound file and the text to force align your phonemes. This one, you can do the textless as well. Basically, it's an ASR task, but on the phonemic level, which I don't think many tools can provide. And this is accessible from Python. You can just use it in Python, so it's convenient for people in tech as well. The languages now, it covers English and Mandarin, but we plan to do more languages. And because we plan to do more languages, we also developed a G2P system for that. Well, we gathered data for that and trained models. So yeah, there are a lot of under-resourced languages here as well. So this is a connected thing. And the other thing is there's another aligner. This is called P2FA. It's a very old aligner, maybe one of the first aligners. It used HTK toolkit, so it's not the state of the art, but I recommend it because for at least Mandarin, I can't remember what was it for English. It can separate diphthongs. So for a syllable like I, normal aligners would only give you the whole diphthong, but this aligner would give you the and the e. So for phonetics research, this might be a more convenient tool. And another one is for extracting F0. There's something called Reaper that my friend in TTS recommended. He said it works very well for prosody. I tried to use it for phonetic research, but maybe for phonetics research, it still doesn't solve the problems that we really worry about. For instance, there are creaky voice where F0 is missing and things like that. So we're still looking for better solutions. So yeah, these are the tools that I recommend. I hope, many of them are aligners, but I hope this is to some extent a satisfactory answer.
Yes, I think so. And I will go ahead with the third question. Would you recommend your career path to others? This is another one.
This is a very difficult question because my career path is very atypical, I would say, because especially because I came back to academia. I know a lot of people who move on to industry after their PhD, but moving back from industry to academia, that's very rare because you get a lot more pay in industry and get probably more freedom. Not freedom, but less stress in industry. So most people would stay. But yeah, crazy person like me, I come back. I probably like the academic freedom more. But whether I recommend people going into industry, I recommend. And it's a very different atmosphere. Yeah, it's fun.
Okay, and the fourth question is, with the advances in deep learning, where we provide raw data to train ASR and TTS systems, having a degree and professional experience in area of signal processing and linguistics useful. I think he means whether having a professional experience in area of signal processing and linguistics is useful.
Yeah, I think it's useful. I mean, if you have the basic skills that can, if you're aiming at an algorithm position, then you obviously have to know everything about that. And on top of that, if you know linguistics, then yeah, of course it will be very popular. Yeah.
Okay, so the next question is from Shantanu, and the question is, what is the role of linguistics in developing an ASR system? And I think, probably Shantanu already has a lot of answers from the talk, and I'm leaving it to Dr. Zhang to answer that.
Yeah. So as I mentioned in the talk, that you can use linguistic theory in ASR, but again, we're talking about very innovative research. If you're in a research position, then you have the freedom to do that kind of exploratory things. But if you're in a company, I very much doubt that you will have the freedom to explore that kind of very abstract ideas. So in my previous company, I did ask the leader of ASR team, and I said, I'm really interested in ASR. Can I be a part of it? Like, can I contribute? But the leader of the ASR team said, well, nowadays ASR is more about signal processing, pattern recognition. We really don't need any linguistics input. But as I said, I don't really agree with that. But I understand his position because in industry, profit is still the main goal. But for research, definitely there are a lot of room for explorations. Not only phonetics, you probably can also get like discourse analysis and semantics, pragmatics included. if someone in the future can create this system which can include multiple aspects of linguistic theory, I think that would do the job. But it's not an easy task.
Yeah, thank you. I will quickly go ahead with the next set of questions. So they are from Riganka. And so the first question is, how can we associate cognitive linguistics or cognitive sciences to the field of speech theory? Which part or aspects of it can be related?
I think there are a lot to learn. Basically, what we're doing is to create, to teach the machine to speak, right? It's the same as teaching a second language learner or teaching a child to speak. The more we can mimic the human system, the human cognition system, the better, I would say. And I think the whole field of machine learning got back, it became popular again because of neural network, which is an imitation of human neural system, right? So I think, yeah, from at least the acquisition point of view, there are a lot of things to learn.
Thank you. And the second question is, can cognitive linguistics or sciences contribute a major part to the development of speech technologies? I think they're very related questions, so yeah.
Yeah, I think it's the same answer really as, yeah.
The third question is, how can we move from basic linguistics, which will include all the subfields of linguistics, to the technical aspects of linguistics or language technology?
I don't really understand this question because I don't know what it means by move. I don't think we should move from one to another. It's more like to combine the two together, to have more conversations, have more communications, have more collaborations, and we work on to reach the same goal together. Yeah.
That makes sense. And so we have one last question from Momita, and the question is, are intonation models sufficient for our understanding of prosody and enhancing the naturalness of speech, of synthetic speech, or is a different approach to prosodic studies required for these purposes?
Yeah, I have to admit I haven't really followed the research in text-to-speech for the prosodic aspect because when I left industry, end-to-end was becoming more and more popular, and the prosody was improved by quite a lot by those models, but they're not controllable and they need a huge amount of data. That's the downside of it. And even when you use the best synthesizers available, like I personally prefer Google ones to the other ones. So I sometimes use it to read a text file or something. And you can still tell, although on the sentence level, the prosody is good, but on a discourse level, the prosody feels somehow repetitive. Yeah, so I think there's a lot of improvement to do. And yesterday I read a paper on, I think that paper started with Intel TTS. So basically they added an intonation component in their TTS modeling. And then what made me a bit, I don't know, is that they used a 1974 linguistic papers classification method from a linguistic paper. And then I just think a lot of the times linguists are blamed for not contributing enough, but at the same time, nowadays the only linguistics input we have in speech technology are from those very, very old days. I also had experience in a previous project that they were using some syntactic features from the 1990s. I mean, it's not that far back, but it's 30 years ago, and linguistics has been developing very fast as well. So yeah, I think that makes us think how to better integrate the two sides of the knowledge.
Thank you. Yeah, I think these are the questions that we have had from before. Sishir, do you want to ask your question that?
Yeah, I think we have a few questions in YouTube chat as well. So I have already forwarded you in WhatsApp. Mike, your mic is muted.
Sorry. So first question is from Sushir, and I'll just go ahead and read it. How to get the phonological features for under-resourced languages?
We will have to look at them one by one. That's the trouble. There is that system called PHI. One of the papers I mentioned in the review. Let me have a look. PHOIBLE. That one has many languages, but yeah, whether it's the best feature set or not is another question, because they have 37 features. So it is still fewer than IPA symbols.
Okay.
Yeah.
And another question, I think, is it difficult to get phonological features than IPA based? Like, for example, we have different G2P converter. You showed a few also in some tools. So directly you can get those G2P phones. G2P, I can say, like, we can say phones, IPA phones. And but here the good thing is that it is language independent one thing, and then number of symbols will be less. But that how to get that, because these phonological features or distinctive features, these are very old like thought process, like because during my PhD also I checked something like if we can apply for pathological speech because people use lots of in lots of research, actually they have explored phonological features in pathological speech. So but the thing is that to get those features is quite difficult. So that's I think in that direction also I think some research is going on. Maybe you'll know better.
Yeah, I think that's a very good idea, actually. Whether this process can be automated.
Yes.
I think to some extent you can, but whether you can do the full thing only using the automated system is another question. Because I think the key point here is to figure out the contrastive features between languages. Yeah. So for instance, for English, you probably only need like half of it. But when you add in another language, you probably need to add a few more, because you have the contrast in between English and that language. And then when you add another language, you probably need to add a few more. Yeah, that's the part that I think, yeah, it really needs some deep phonological knowledge to be able to work out the system.
Yes, exactly. Like in some cases, like most of the languages, we have voiced nasals. Like Pamir, she works something on voiceless nasals, for example. So that is totally voiceless. So this is a different category of nasals. So, but in most of the languages, we don't have that category of phones. So
Yeah.
if we want to add that particular low resource languages to this particular to get the phonological features for that particular language, it will be quite difficult at that time. So maybe that may be a good, I think, way of research direction. Yeah, Pamir, you can go ahead.
Yes, that was a very relevant point. I'm still struggling with phonological features for the languages I'm working on right now and for TTS. I will go ahead with the next two questions by Nannan. So the first question is, so he thanks for this very interesting, sorry, I'm just, so the comment is first a thank you for the very interesting talk. And two questions. First one, your input embeddings are phonemes and prosodic phrasing features, and how do you account for the voice quality issues in the input?
The phonological features can account for the voicing. It's one of the. Do you remember that tree? One of those features can deal with the voicing. Yeah, if I had a link, well, maybe afterwards we can go back to the video that has all the features. Or maybe I can show it to you now. So yeah, if you go to this link, then you get the whole set of phonological feature mapping. Or if you look at this this graph, you have the, well, because we wanted to show it in one page, this is the only way. Yeah, voice. There's a voice feature, so if it's voiced, then the voice feature would be 1, and if it's voiceless, then it would be 0. Yeah.
Okay, thank you. And the second question is, I noticed that the input sentences are quite standard, almost written-like. Will the accuracy of the systems decrease due to accents and disfluencies that are common in spoken languages?
I think definitely will. Because, as I said, this is only our first step exploration. Our main research question before we did this was, will feature work? Because this is dramatically reducing the number of labels. We were not even confident that it would synthesize intelligible sentences, but in the end it did. So we were quite happy with that. Naturalness and also, under different circumstances. These are all future research topics. Yeah, but thank you for mentioning these.
Yeah, that's amazing questions and a very great session. I thank you so much for this amazing session and giving us your time. Sishir, is there anything you want to add?
No, I think that's great. Excellent session, Kong. Maybe I pronounce your name wrongly. So yeah. So we don't have any other questions. So
Okay. So okay, should we wrap it up? Someone will.
yeah.
So yeah, thank you all the audiences for raising these questions, and thank you again for organizing this event and inviting me.
Thank you so much.
Thank you. Sasank, maybe you can stop. So I'll stop the streaming.
Okay, sure.